Hello, dear students. I'm going to explain the effect of the Earth curvature and refraction. We suppose that the Earth is a sphere, and we are going to consider the long distance between the instrument and the leveling staff. When we are going to put our instrument on X and we put our staff on B, we put our instrument on X, and the height of instrument corresponding to the distance x prime, and the line of sight is supposed to intersect the staff at B prime. From that, as A and B are on the same level, we have B prime are equal to the height of instrument. It means that the distance between B prime and B second constitute the error, and this error is called error due to the curvature, which is symbolized by C. But from that, we know that according to the atmospheric conditions, the rays are refracted, and we read on Y and not on B prime, and this is going to introduce another error due to the refraction, and is symbolized by R, and the combined error is equal to the distance between B prime, B second minus the distance R. And we have here R, which is the radius of Earth, and the direction of gravity. How are we going to estimate the error due to the curvature of Earth and the refraction? If the instrument heights are ignored and the Earth assumed to be spherical with the radius R, you are going to consider the triangle 0 OX B second, and from that X B seconds square is equal to this one O B second square, which is equal to radius plus the error due to the curvature squared minus R squared. And when you are going to develop it, you are going to trust that you have R square plus 2RC plus C square minus R square, which is equal to 2RC plus CR, where you have R squared minus R squared is equal to 0. As both C and the instrument height are relatively smaller compared to the radius of the Earth, the distance X prime B prime may be assumed equal to the arc distance XB, which is equal to D. Therefore, the distance D is equal to the square root of 2RC plus C square. Now, as C is very small compared with R, C squared may be ignored, giving C, which is equal to D square over 2R. And you are going to consider the distance in kilometers, and an average value of the the radius of Earth equal to 6,370 kilometers, and we have C, which is equal to D times 1,000 squared over 2 times 6,370 times 1,000, and when you calculate with your calculator, you realize that we have 0.078 d square, with the value of C in meters when D is in kilometers. Let us take the example here in this table. We suppose that the radius is equal to this value, and the distance we start by 1,000 meters, which is equal to 1 kilometer, and 500 meters, 250 meters, 125 meters, and 120, and 100 meters, and 50 meters. And the value to be used will be converted into kilometers. And then we have the formula here of computation of the curvature error. And when you are going to replace 0.0785 times the distance, you are going to obtain the value here. What we are going to realize, when the distance is decreasing, you see the error is decreasing. When you have on the distance of 125 meters, the error is reduced to 1 millimeters. And when we are on the distance of 100, we realize that we are below a millimeters of error, to mean that we can allow the distance to choose the distance according to the accuracy of measurement we need. For the distance equal to 50 meters, we have 0.0002, to mean that the 2/10 of millimeters, which is very, very small, approximately equal to 0. This the reason why you are going to consider that is when you have the small distance approximately equal to 50 meters, this error, capture error, is approximately equal to 0, and can be neglected or can be ignored. Dear students, as explained before, the staff reading would not be at B prime but at Y because of the refraction of the line of sight through the atmosphere, and this will reduce the error of curvature with the distance r between Y and B prime, and this error is generally estimated to 1/7 of the curvature error. Therefore, we have the combined effect of curvature and refraction, C minus R, which is equal to 0.0673 times D square. Please take your calculator, and you are going to take you take 6/7 times 0.0785 times D squared. You are going to obtain 0.0683 times D square. If you are going to calculate the values, we realize that from 1,120, the combined error is equal to 0. And according to the accuracy required for our works, we can ignore the combined error. This combined error can be ignored when the distance is small, and when the staff reading are kept at least at 5.5 meters above the ground to avoid the refraction. When you are going to use the equal distance between back side and fore sides, we are going to eliminate the error of collimations. It means that observing those conditions, we have eliminated all the errors that can affect the measurement of the elevation or the height of our point. Thank you for your kind attention.